Hi everyone, welcome to part 2 of strengthening mechanisms in metals. In this part of the lecture, I'll cover the 4 remaining mechanisms for strengthening a metal beyond strain hardening, as defined by an increase in the yield strength. Where we left off last time was describing how imparting plastic strain can increase the yield strength. We discussed this both within the context of dislocation density, as well as with a more empirical approach, cold work. The relationship between stress and strain is often captured using the Holloman expression shown here, which expresses the rate at which the strength increases with strain according to a power law expression. K and N here are empirical constants. A safe assumption for many materials and loading scenarios is that there is very little effect of the rate at which plastic strain is built into the material. That is, both K and N remain the same throughout. The effect of strain hardening on stress is captured by this expression. We will spend the remainder of this part of the lecture discussing the mechanisms or techniques that are conducted to A. Change the strength, and B. Change the rate at which the material hardens. Barriers and impediments to dislocations moving. As we covered in the first part, there are strain fields associated with dislocations. In the example given for an edge dislocation, there is a compressive strain field on one side of the dislocation which is balanced by a tensile region on the other. Substitutional alloying additions, which are either bigger or smaller than the host lattice atoms, can also have strain fields associated with them on the same basis. In the instance where the atoms are larger, there will be a net compressive field surrounding the atom, with a tensile field associated with the smaller one. These fields, which are attributed to substitutional additions, can interact with the respective fields associated with dislocations. Similarly to how a pair of dislocations with the same orientation are brought into each other's influence, their fields will repel. If there is a compressive field associated with a substitutional atom, then this will repel the compressive field associated with the dislocation. Interstitial alloying additions, that is, those that do not replace atoms in the overall lattice but remain in solid solution residing in interstitial sites, can also have an effect on dislocation mechanisms. These interstitial atoms often migrate and reside at the core of dislocations. This has the effect of reducing the overall distortion in the lattice, and therefore reduces the magnitude of the tensile and compressive regions surrounding the dislocation. This results in it being harder to move the dislocation from this point, as more shear is required as compared to a dislocation without a pinning atom. An important example of this is carbon and nickel additions to steels. These are the two routes for solid solution strengthening. They are different in the specific effects on dislocations, but employ the same tactic. By alloying additions, they create circumstances where it is harder for dislocations to move by locally distorting the underlying lattice. Note that these solid solution effects are appreciated at the smallest length scale and interact with individual dislocations. Moving up on the length scale, alloying can also be used to create barriers to moving lots of dislocations. Consider the following section of a phase diagram for the aluminium-copper system. For a 4% weight copper composition, if equilibrium conditions were adhered to, then at room temperature we would end up with a solid two-phase composition, alpha and theta. If we were then to heat up this composition into the single alpha phase region and very quickly cool it with a quenching operation, we would end up with a supersaturated solid solution of copper and aluminium. Upon slightly raising the temperature and holding for a period of time, this quenched structure would slowly evolve some theta as the copper slowly diffuses out, reducing the degree of supersaturation. That is, a non-equilibrium precipitate of theta would form, depending on how long it was aged. By changing the aging schedule, both the distribution and size of the precipitate that forms can be controlled. For extremely fine, evenly distributed precipitates, the dislocation will need to cut through them in order to pass. If they are large and spaced further apart, then the dislocation will bow around them. This is the third method of strengthening, called precipitation strengthening. The underlying physics deciding either bowing or cutting are beyond the scope of this course. However, there is a competition between the two in terms of how effective either cutting or bowing is for preventing a dislocation to pass. At a simplified level, this is down to the size of the precipitate that forms. The competition between cutting and bowing and the relative contribution to strengthening, either by yield strength or shear to move a dislocation past a series of precipitates, can be represented by this plot. For very small precipitates, it is easier to cut than to bow, and past a critical size, it becomes easier to bow than to cut. To the left are examples of both. On the top right, large precipitates on the order of tens of microns have been cut and sheared by passing dislocations. Below this, on the order of nanometers, a dislocation line is bowing around much smaller precipitates. You can see that where the precipitates are closer together, there is significantly more bowing than where they are further apart in the bottom right. On the micrograph depicting cutting, you can also see that the relative amount of translation of the precipitates that have been cut is much higher where there are fewer of them. This is a secondary aspect of precipitation strengthening, the mean distance between each precipitate particle, which isn't captured here, only the size. However, precipitation heat treatments, solutionizing, quenching, and aging, will target a specific size of precipitate, such that both phenomena can be taken advantage of to achieve peak strength. The fourth strengthening mechanism is to reduce the overall grain size. When I covered plastic behavior, I described how dislocations will start to move in grains which are best aligned with planes of maximum shear. As the stress increases, more grains start to slip, and the dislocation density increases due to dislocation interaction and piling up of dislocations at grain boundaries. By increasing the number of grain boundaries, more dislocations will pile up at these locations, and therefore locally increase the dislocation density at these sites. There is a very famous expression which captures the relationship between yield stress and grain size, the Hall-Petch relationship. It states that the yield strength is inversely proportional to the square root of the average grain size. Here, d bar is the average grain size, or the average of all of d1 through 4 on the left diagram. The slope of 1 over the square root of d bar is the Hall-Petch coefficient, k. Some materials will have steep or shallow slopes, steels and aluminium alloys, for example, respectively. But for very small grain sizes, there will be a steep slope. This is because the overall strengthening effect is both the resistance to dislocation movement within the grain and the length of pile-up dislocations at grain boundaries. When the size of the pile-up starts to encroach upon the size of the grain, the yield stress will be extremely high. The last strengthening mechanism is that imparted by non-equilibrium phase transformations, the finer details of which will be covered more in depth when we discuss steels, but I will briefly cover concepts here. Steel, above a particular temperature, will exist as a solid phase called austenite. If one were to cool very quickly from this temperature, called the eutectoid temperature, then the austenite would transform to a metastable phase called martensite. This metastable phase cannot be represented on a phase diagram, but it can be on a continuous cooling diagram as shown here. By cooling very, very, very quickly, we have essentially switched off diffusion. Recall that steel is a metal comprised of iron and very small amounts of carbon. By switching off diffusion, there is no transport mechanism to allow carbon to enter interstitial sites of the BCC unit cell, and it will therefore elongate to become non-cubic to accommodate the carbon atoms. This has a dramatic effect on dislocation movement. BCC crystal structure already has a limited number of slip systems, and this shift in unit cell will affect these dramatically. Furthermore, the microstructure, that is, the grain level structure, will also be significantly refined, as shown in the micrographs on the right. On the top, a stable microstructure that is obtained under near equilibrium conditions, and below this, a metastable martensitic microstructure. So that rounds out all 5 mechanisms with which to strengthen a metal. In the first part, we described the first method, which is independent of microstructure, or is something that can be applied to all different microstructures, with the response being a function of each. In this part, we covered an additional 4 mechanisms that rely on microstructural modifications. These were solid solution strengthening, precipitation strengthening, grain boundary refinement strengthening, and finally, transformation strengthening. For all 5 mechanisms, there is a trade-off between increasing the strength, by impeding dislocation movement, and ductility, allowing dislocations to move freely and permit slip to occur. These mechanisms described do not operate independently. Often alloys will take advantage of some or all of these. For example, precipitation strengthening will invoke solid solution strengthening. This is because of the differences in length scales on which they operate. Depending on the underlying crystal type, alloying, and other factors, some techniques will be more effective than others, or will be more affected by subsequent processing. Until next time.